Let's start with some motivation. Protocol IPv4 was great and still works, but unfortunately the available addresses space wasn't sufficient to the number of addresses required in the industry. And the number of addresses required by the Internet of Things and mobile IP wasn't sufficient. And therefore there was a need to move on to something with more addresses. Instead of a 32-bit space, to something bigger. In the case of IPv6, it has a 128-bit space. Router manufacturers had an additional motivation as they wanted to decrease routers' overload. The routers ran many checksum checks and kept doing IP fragmentation, which of course overloaded the routers and their performances. This is the reason IPv6 protocol was suggested, a protocol that includes fixed-length 40-byte headers with options, without checksums, and with no fragmentation done in the routers. Fragmentation is still allowed at the edges. To be able to avoid fragmentation, IPv6 protocol performs MTU path check from edge to edge in order to ensure that a situation that required fragmentation doesn't arise. In IPv6 datagram format, the fields are version, which will probably be 6, priority, which is bits that allow giving priority, similar to type of service bits in IPv4. Flow label is an identity that allows to mark the flow dedicated of some packets with a particular color or number, and is later very helpful with the quality of service or with packet classification for another purpose. Payload len is the packet size in octets. Next header is a type of header that comes after the main header. It can be, for example, a header with IPsec, security, and any other header. Hop limit replaces TTL. In essence, it's a name change. The role is not changed. And there are two addresses, source address and destination address. Each has 128 bits. Afterward, there is data. But as we have already understood, it may have an optional header of IPv6 itself. In the slide, we don't see anything related to checksum, and we don't see anything related to fragmentation. Although in the case that fragmentation is done at the edge, which is allowed, we have an option to add a next header, which would be a header responsible for fragmentation in IPv6 as well. We should remember that there is no fragmentation in the routers. There is fragmentation only at the edges. What are the changes from IPv4 that we talked about? Because the transmission's quality has improved and the physical layer and signal identification have improved as well, the chance to change a 0-bit to 1 and vice versa has decreased. Therefore, we are able not to deal with checksums at all. Now, options are rare. Usually they are not executed as options, but rather as a next header field. ICMP v6 is a new version of ICMP that has a smaller role than ICMP v4. Its main job is to discover errors, and some of the roles of the ICMP and ARP have moved to Neighbor Discovery Protocol. Another important feature in IPv6 is that every IPv6 computer on startup immediately assigns itself an IPv6 address, which is a local scope address. You can use it in the internal network, and therefore a computer with IPv6 always starts with some address that can be used for various purposes. Transition from IPv4 to IPv6. As of today, there still exists both IPv4 and IPv6. IPv6 traffic's share, according to recent data, is about 30%. And most of the web, especially infrastructure network, is IPv4. Internet providers and the large companies that maintain internet infrastructure are in no hurry to move on from IPv4. They invested a lot of money and a lot of equipment. Therefore, we have a situation in which we need to transfer IPv6 datagrams between units that don't support IPv6, such as routers. There could be a chain of IPv4 routers that doesn't support IPv6. So, how do we solve this? We treat IPv6 datagram as data and encapsulate it with an IPv4 header. That is why it's called tunneling. What is tunneling? You're supposed to transfer in a certain media something that can't deal with that media. You encapsulate it with something external that knows how to move through that media. It's doing tunneling and then removes the encapsulation. Therefore, the IPv4 header's role in IPv4 IPv6 tunneling is to transfer IPv6 packets between IPv4 points, and later they are removed, and can keep moving in the IPv6 network freely. There can also be a reverse process. This can be done as well, and there is a tunneling process of IPv4 packets in an IPv6 network, such as we see here. We have two IPv6 areas connected by an IPv4 network, and we keep going. We add the media in order to do tunneling. And once we're done, we remove the IPv4 encapsulation.